Hello students, welcome back. Let's resume our discussion from section 2. We went through an angle example, and those are rather special. We went through 90 degrees and 180 degrees. Let's generalize this a little bit further. If the cosine of theta is 0, then that means the numerator is 0, so dot product is 0. In that case, we have 90 degrees. So two vectors are perpendicular or orthogonal. They mean the same thing, orthogonal or perpendicular. When cosine of theta is positive or negative 1, that means the angle is 0 or 180 degrees. In that case, they are parallel. So the numerator and denominator are the same in terms of the... Oh, excuse me, sorry about the typo here. What I meant was 180 degrees, not 1000 and... Sorry about that. Where was I? Yes. The numerator, the dot product, and then the denominator, the product of the magnitudes, are the same in terms of absolute value. That means you have either 0 degrees or 180 degrees. In that case, they are parallel. Now for parallel vectors, it's going to be a lot easier to consider scalar multiplication, as you see in the right-hand side here, which I'm highlighting in bold right now. So this one is going to be used more often. As for orthogonal vectors, this is what we're going to use. The dot product is 0. Let's see, do we have some example here? Find the x values such that the given vectors are orthogonal. Okay, how about this? Okay, all right, x comma 1 and 4 comma x. So the dot product has to be should be x comma 1. The dot product has to be 0. So x times 4 and then 1 times x has to be 0. What do you get? You get x equals to 0. That doesn't look too good. Did I make the problem wrong, or is this really the problem? Let's see, what do I have here? Indeed, x equals to 0. Stupid problem. In that case, when x... excuse me, x equals to 0. Perfectly fine. Sorry about that. X equals to 0. 0 comma 1. Yeah, I mean, it doesn't mean the vector is a 0 vector. Just x coordinate is 0. And then 4 comma 0, yes, blue and red. Sorry about that, I was momentarily confused. Sometimes if the answer is 0, then sometimes my first reaction is, hey, this is too simple. But sorry, it's okay, as you can see in this picture. So x comma 1 here is vertical vector, highlighted in blue. And 4 comma 0 here is horizontal vector, highlighted in red in this case. And as you can see, these two vectors are perpendicular to each other, or orthogonal to each other. How about the next example here? xi plus 2xj versus xi minus 2j. Well, I use ij expression, but the dot product computation is pretty much the same. Dot product of this one. So multiply the x coordinates, x squared, and multiply the y coordinate, 2x times negative 2. That has to be 0. Okay, so what do we have here? X squared minus 4x equal to 0. Factor x out, x minus 4 equal to 0. So we're gonna get x equal to 0. Oops, sorry about this typo. Or x equals to 4. Those two cases. X equal to 0, okay, in this case, x equal to 0 is going to be a trivial case. Plug in x equal to 0, then this vector, which I just highlighted in green, will turn out to be 0 vector. 0, 0. So that's a bit trivial. Now, if I plug in x equal to 4, then everything will be fine. Let's see. I don't need this anymore. I don't need this one anymore either. So x equal to 0 or x equal to 4. And yeah, that's okay, but you cannot draw it because this green vector is a trivial 0 vector. You cannot see it. If you plug in x equal to 4, then we have a non-trivial case. Yeah, you can see it. So 4, 8, that's blue vector here. And then 4, -2, that's the red vector here. Oh, they're already highlighted here. So blue and red, they're perpendicular to each other, as you can see here in this visualization. So what did we go through? We went through the orthogonality condition. As for parallel, let's see, how about this? Find the x values such that these two vectors are parallel. Well, let's go back to this condition here. You can use cosine of theta is 1 or -1. We can do that. But it's going to be a bit more convenient to do it this way, using scalar multiplication. So the first vector is some scalar times second vector. What do you mean by that? Left-hand side x is 4 times k, and the second left-hand side is 1, that's k times x. So we ended up with a system of equations. So let's see. X is 4 times k. So plug into the second equation. I'm getting 1 equals to 4k squared. You see, this is 4k multiplied by 4k here. So k times 4k. So that's 4k squared. So I'm getting k equals to 1 over 4. K squared is 1 over 4. So k is 1/2. K is 1/2, or -1/2. Did I do this right? So x value is gonna be 4 times 1/2, or 4 times -1/2. X is 2, or x is -2. Looks like that's the conclusion I'm getting. Did you follow? Or maybe I should have solved for x and plugged in without looking for k value. Maybe that's what I did here. Yeah. That's what I did. So for k and then plugged it in. So 4 equals to x squared, so x is plus or minus 2 instead of looking for k and then coming back. So this solution is a little bit more efficient than what I did earlier. And is there visualization? Okay, all right. X equals to 2, 4 comma 2 versus 2 comma 1. As you can see, they are parallel. And this time 4 comma negative 2 versus negative 2 comma 1. Again, they are parallel, even though they are now in the opposite direction. So, parallel vectors, we can use scalar multiplications. For orthogonal vectors, we can use the dot product equal to 0. Let's see, do we have time for this? No. I'm gonna leave this problem to you, so start the playback and then do it on your own. Did you do it? What do you have? First vector is k times the second vector, and then set up a system of equation. X is kx, 2x is negative kx, so k is equal to 1. And plug in, you get x equal to negative 1. Another case is x equal to 0 from here, and then x is 0, k is 0, everything is 0. That's just too trivial. So x is negative 1, then plug those in, we get negative I minus 2j, so negative 1 comma negative 2. And then the other one is the same, actually, negative I and comma negative 2 again. We have some further properties of those dot product with the commutativity, or it's called symmetric, and then distributivity and associativity, sort of, and those are called bilinearity. And then this property is called positive definite. The dot product is always strictly positive, except for a special case when you have 0 vector, and multiplying by 0 is always 0. Yeah, I guess those are just trivial, something that we had been taking for granted for all kind of multiplication. So I don't think they're going to be too much of a deal. And that's where we're going to stop. There's no reason to go too much into this. And if you're interested, you can always go back and study that pre-calculus textbook. If you're preparing for math teacher exam, the Texas exam, in that case, you have to study vectors and high-dimensional analytic geometries a lot, because a lot of problems are coming from there. And UNT Dallas calculus does not cover it very well, so you will have to go back to pre-calculus and study that. Otherwise, let's draw a line here. We'll say all is done. And then I'll show you some fun demonstrations in section 3 in a separate video. That's it for first week.